Alright, let's look at an abridged version of how to create training data from MP3s. You can see in some other videos to where I actually go through when we wrote this notebook and setting things up. This time I'm just going to skim through it in a quick fashion and kind of show you the highlights. So we got NumPy and TensorFlow. We have this library from Nayuki that has fast Fourier transform functions in it, and we're grabbing this transform function out of it. He wrote this great site, UKI, Yuki.io. And apologies if I'm butchering the pronunciation, but anyway, there's code in here for many different languages to create the fast Fourier transform. And it's great. So incorporated this because another part of this project we're using it in JavaScript, and so there's the exact same code in JavaScript and in Python to process the audio in the exact same way. So using that here just as our custom way to make these spectrograms. Anyway, we're also grabbing in Google Cloud Storage because that's where the MP3s are stored at. Getting pool from multiprocessing so that way we can parallel process all of this training data. Our sample rate we're setting to 16K, again because that works later on whenever we're using this in JavaScript. Setting NFFT to 1024, so our spectrogram heights are going to be half that of 512. And so we're specifying that here, 512 by 512, so pretty much taking block spectrograms. It's skipping every 256 units over those. Max seconds to 120 seconds, so 2 minutes of audio per file max, otherwise we're truncating it. And then per asset class, we're grabbing up to 25 training files. So it's at 50 minutes of training data possible per bird. Okay, here we already created this FloridaBirds.json file that has 105 different birds and all of the audio files that go with each one. So we saved that to this JSON file and we're just going to load it up here. Scores we're going to ignore for now. Later on we actually train a model with this big spectrogram, and then we go back through and process all of our training data, compare it to what that model classifies for it. So, and then we only keep the ones that match. So for example, if an audio file from a class 10 bird of class 10, whenever it goes through the model, it comes out as like a class 8, then we're going to ignore that section of training data. Not the whole file, but just that portion. Anyway, that's later on. So we grabbed our Florida birds and number of classes. We have this function here that downloads it. It's really a WAV file. It's named .wave, or it's really an MP3 file. Anyway, we download it. We use ffmpeg to convert it to a 16K WAV file with one channel. So condensing 2 channels down. So again, just standardizing everything to a 16K mono. Here's where we're creating our spectrogram for it. So we're just creating a list, and then we're going through our audio data every half NFFT units. So every 512 units, we're skipping over it. Not skipping over it, we're going over it. And then we are sending that data to this transform function that creates the fast Fourier transform, getting the spectrogram back from it, and adding that to our list. Then taking the log of it, reshaping it, taking the transposing it so that way it flips it around, and also making sure that all of our numbers are valid. And then we're dividing it by the mean of that spectrogram, just normalizing it out to kind of account for different volume levels, different microphones. Just normalizing it all. So those are our 2 main functions. Download the MP3 to create a wave, take that wave data, and we're sending it in and splitting it up into chunks to create spectrograms from it. And then we send back one big spectrogram from the entire file. Alright, so here's our main processing function that's going to remove these 2 directories, and then we have this function here called getBird, and this is going to be our function that we're going to run in parallel. So for however many cores that this computer has, let's say we put 64 cores on it, we're going to run this 64 times in a row not in a row, but at once. So that way we can process 64 classes of bird at one time. Just to kind of speed it up, because it takes a little while. So in order to kind of space things out so that way they don't all start at one time, whenever this function starts up, it's going to sleep for some random amount of 10 seconds. Then we're just grabbing some metadata out of the argument passed in, which is the bird index and the item. Then we're creating a directory for that data. Yeah, just getting the bird name here, printing it out the screen. Then we're getting a list of all of those asset files. And then we're just going to enumerate through them. And so for each asset file, again, I have some stuff in here for the scores. And we're going to keep that. Yeah, I'm just going to ignore the score stuff for now. So we'll keep the try and wave, keep that. There's one other place down here. Right here. Okay. Again, this later on, we're just filtering the audio down there, and this is an example of what we're doing the first time around. Kind of a quick look at the other videos that we made. So showing how quick or how we would initially make that audio data, the spectrograms from all that audio data. So before we would have a model to actually compare it to. Anyway, so we're looping through, create the directory, grab the bird, grab the audio files, and we're just printing out the asset index as a way to track kind of where it's at. We download and convert that file to the wave, calling that function that we have above. Just in case it errors out, we have a 10-second timeout and we try it again. And then we just skip over and run to the next asset. Every now and then from Google Cloud Storage, you can get like an SSL error, or I don't know. I don't know if I'm calling it 64 times in a row and it just gets angry at me. So that's something to at least catch that error. Okay, so here we are reading that WAV file that we downloaded. We're converting it from an integer to a float. We're doing that just dividing the number by the max int16 value in NumPy. Ensuring that it is a float 32, because when we originally make this operation here, it's a float 64. Then we're calling that get spectrogram, create spectrogram function from above. Yeah, that just loops through all of the audio data, creating the spectrograms, because we're going in at sample rate times the max seconds. So, because if we have a sample rate of 16,000, that means that every second we have 16,000 data points. So we're allowing 16,000 data points times 120 seconds, 2 minutes of audio data, going into that create spectrogram function, which spits out a spectrogram. Okay, and here we are going from, let's see, the window index. Oh, yeah, window index, start index, because we're enumerating through that spectrogram, or the length of that spectrogram, going over by skip units at a time, right? So we're just enumerating of this range that we're starting from 0 to the spectrogram shape of -1 width, skipping by skip units. Again, ignore that code right there. Spectro just then takes that spectrogram in that little chunk from wherever we're at to where we're at plus a width. So in this case, 512. Opening up some file that we're naming in a directory, yeah, our spectrogram directory, then the bird index with the asset index and the window index, just so we can find it later on. And we're taking all of that audio data that we had and we're just reshaping it to a string and making a CSV from it. Quickest, easiest way later on to read it back out, or at least for me, from what I know for right now. Okay, moving on. So we have bird items. We're going to create this array from all of our list of birds. It's pretty much just a tuple that includes the index and then the information for that bird. Just so it's easier to call here. Then we're creating a pool with our 16 cores, and yeah, mapping our function over it. So we're taking this list right here, mapping it over our 16 core in the pool. Yeah. mapping that list against getBird. So it's calling it for each of the 105 bird classes. So that runs and runs and runs and creates all those spectrograms. And then let's see. Here's an example of what those kind of look like. What we have done here is for I in range 25. What are we doing? We're just going through the first 25 spectrograms for the 0 class. So it's the cardinal, and printing out what they kind of look like. Which you can do just by grabbing the spectrogram. We're reading the file and splitting it on the comma. Then here, I'm putting it into an NP array. And then here we're just converting that to a float 32 and reshaping it to the 512 by 196. 512 by 512. It's 196 whenever I ran this. Okay. So here is where the TFRecord part begins, right? What we're going to do is just remove our two TFRecord directories, or our TFRecord directory, and then recreate it. So there's no confusion about what we had or what we have now. And in a very similar process to what we just did above when we created these spectrograms, we have a function, and then we're going to create a process pool and map some list over that function. In this case, it's just a range of 16. And so what's going on here is we're creating 16 different TFRecord files, and each one has examples in it, training examples. And we're going to randomly select each one of these examples as we're writing this file, so that way when we read the file back out, everything's already randomized. We just kind of stream it from disk to the GPU. So this is how that works. Print a statement just saying where we're starting at, and we create a TFRecord handle, like a file handle, using this function here, the TFRecordWriter, which just takes a string for where that's going to exist. And then we are looping over a range of 5400. Looking in the command line earlier, that's how many different spectrogram files we have. So we're just going to use that as a reference point. So each TFRecord file is going to have 5400 examples in it. So in other words, we're taking the current amount of data that we have and we're expanding it by 16. The main reason for this is because of what we're about to do next, as we are randomly selecting all of our training data in that file. We're not just iterating through it in the list. We're not shuffling it and then making sure that each item's in there. So I wanted to expand it out since it was randomized, just to give every example an opportunity to be in a TFRecord file and to have them split out more, so that way it's just offers more entropy, more randomness there. Okay, so again, we are checking every 100 indexes and printing out some status. And here we're grabbing our class index. So we're just grabbing a random integer, somewhere between 0 and our number of classes, exclusive. So it's from 0 to 104. So 5400 times we're randomly selecting one class. Then we're going and getting all the spectrograms in that folder for that class, and creating a list from that. And then we are using, again, NP random choice to randomly select one of those spectrograms. And then we are taking that file, opening it up, mapping the float function over it, converting it to a list. So we still have a one-dimensional list, but of that spectrogram, at least in float format now. And then here's where the magic of actually writing that TFRecord, or maybe not the magic, but the actual process of how to do it. You create a dictionary. The keys can be whatever you want. In this case, I made one called class and one called spectrogram. And then you can put whatever data you want in there, so long as it is in one of the formats that a TFRecord file accepts, which are pretty much like Int64s, float 32s, and you can have a byte string. So you can put strings in there, but here we're just dealing with integers and floats. And both are a tf.train.feature, and then it depends on the argument that you put in, an int64 list or a float list. And then you just set that equal to the value that you want coming in. So it's a tf.train.int64 list, or down here, a float list. And above in the class key, we're just giving it the answer, right? The class index. So we're setting the value to a list of one item. That's the class index. Has to be a list. I think a squirrel just fell down off the roof. Anyway, so here's a float list of our spectrogram. We're just setting it to the value of the spectrogram. Okay, so we're creating an example prototype, example proto, and tf.train.example, and then features equal tf.train.features, that feature from above. So the syntax is a little redundant. Like I copy and paste it every time, but it works really, really well. And then we're just writing that one example called serialized to string. Throws it in the file, and then later on when we read it back out, we do have to tell the format that the data is structured. So we have to give it a very similar dictionary to this. And it parses that data back out, but it does it very fast. So anyway, this is our writer, and then we're creating another process pool of 16, and we're mapping just some list of 16 numbers, each one being a task index for the file name of the TF record over that function. So that runs here, and then you have TF record files that you can go and train with. If you found anything to comment on, let me know. Anywhere that I messed up, I probably messed up at least a couple places. Let me know, or the ways that I could do this better. Yeah, but I like TF records. They come in really useful, especially for memory management and process management. And randomizing them here, I don't know if I've ever done it to this extent. Just randomly selecting examples to put in. Normally I would do it more like a shuffle method, and then just iterate through that shuffled list. But I like this method. It's kind of a lot quicker for me to run through. Anyway, thanks for watching.